Hello and welcome to TidyX episode 58. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick. And TidyX is, of course, on Twitter at tidy_explained. You can also email us if you feel better about that, tidy.explained@gmail.com, or comment on the YouTube channel as one of our viewers did last week and gave us some great ideas, which we will use today.
Yes, thank you so much, Mike.
Thank you so much, Mike Parrott. Or you can go on the GitHub repo and you can open an issue. I think I have 2 or 3 issues in there. Mainly they're issues with Ellis, not necessarily the screencasts.
Seems reasonable. I'm a horrible person.
Yeah. So what have we got today?
All right, yeah. So we are continuing our series on pitch classification, and this time we're going to be using a model that I think everyone has heard about because everyone on the media, you know, if you're in computer science or in data science at all, you've heard about this, got a little hyped about it. We're using deep learning today to do pitch classification.
Yeah.
All right.
And we're going to find out, is the steak worth the sizzle?
Yes.
Is it
worth the effort?
Yeah. Is it worth the effort? Which is an important thing to always ask. Just because something's hyped doesn't necessarily mean it's better, right?
All right. Yeah, cool. So I will share the screen with Patrick so you can see what we're talking about here. Share screen, share. All right. So, boop, pop that up here. But as always, we're going to start using our Markdown. We've got our title and everything here. As a reminder, we are using data from the MLB Game Day, data collected by the MLB Game Day package. We are using pitchfx data. If you want to learn more about that, go to this link here or read a paper from David Kagan, resource of the features of pitchfx data. Also, background. We were hired, not really, by the Fantasy Baseball League to predict which pitches are being thrown. Traditionally, human stands in the back or in the stand, sits in the stands, and writes down. Okay, this was a fastball. This was this. This was a changeup. They want to productionalize it. They want to get that person to doing more productive things. So they hired us to come up with an algorithm to make predictions.
Yep.
All right. So we're going to start with the loading of data. So we're going to be setting our base path here, which is just going to be the location in our repo where everything is. You can once again access it at the bioengineer./tidyx, and we're going to only load in at this point in time the tidyverse package because we're going to load in the deep learning packages in a moment. Next, we're going to load in the data and do some cleaning. We're not going to go through that. We've covered this very in depth in episode 53, so you can check that out at bit.ly TidyX episode 53.
Exact same steps that we've done for the past 5 or 6 models that we've built.
All right. So now that we've got our data prepared, at least initially, we're going to define the model that we're going to be using for deep learning. All right. So one important piece and unique piece of the deep learning, and we're specifically going to be using the keras package, which also implements TensorFlow, is that you go through and define, this is how my model is going to be built up. Because a deep learning model is built up with a bunch of different layers that are stacked upon each other, that have different weights within them. It's very magical, black boxy, to me at least. And,
super black box.
And eventually you end up with this final, what they call output layer, which is where the actual predictions come from. So let's take a moment and step through this. So first we're going to load the library keras, which is, I think, supported by RStudio folk. So we know it's high quality. If you've not done deep learning or loaded keras before, you're going to need to load all the deep learning magic mumbo jumbo that goes on in the background behind it that makes it run so quickly. So you're going to have to actually run keras : install _keras, and it'll install all the background stuff that you're going to need to know. Go to RStudio's website if you want to learn more about how to get that set up. So we are going to be creating what's called a sequential model. for this model here. So a sequential model just means layer after layer after layer after layer. And it is the most straightforward version that we could come up with. There are a lot more complicated deep learning, like if you're hearing a BERT or for like NLP stuff or all these other deep learning and AI algorithms, they're probably a lot more complicated than this. Go in and do some reading on this if this is something you're really interested in doing, because it's very interesting. There's a lot of work going on right now in this. So like I said, we're going to do a sequential model, which is just layers built up one after the other. And so keras actually provides a handy dandy helper function to get your model started. It's called keras model sequential. So we're going to run that, and now we've got our model object. And so you may see at the very bottom here, there's a bunch of messaging that's going on here, because it is actually connecting to Python in the background, which is connecting, that is going to be implementing this deep learning for us. So all of this is a bunch of mumbo jumbo that doesn't really matter to us since we're using R. Unless it throws an error, in which case that's an issue.
Yeah, then it's a problem.
One other unique thing that I wanted to bring up too, very, very briefly, is this model gets updated, right? So normally when we're running something in R, you have to assign the output back to the same object itself if you want it to be overwritten, or a new object, and that's now the new value. With this setup, model, anything you do to that model updates itself. And so that is a very important piece to keep in mind as you work on this, because you can't just keep on retraining your model, because it's going to be using the end state from the last fit. If you want to redo it, you have to rebuild your model. Mm-hmm. Just to be clear about what's going on there. All right, but now we're actually going to define the layers that we're going to be doing, which is the magic of deep learning. Patrick, you want to take us through this?
Yeah, so it's actually, the keras package makes it quite simple. You take that sequential model and you pipe in first the number of hidden layers that you want. So these are basically the layers that are sitting between the initial data that you're feeding the model and the outcome, or the output, the prediction. And so we just have 2 hidden layers, but you could have, I mean, people make deep networks with hundreds of layers, and this gets complex really quick. So we kept it simple. We have 2 layers, exactly. We have 2 layers. That was like 20 layers or something. much that would be deep. That would be a deep neural network. So we have 2 layers, and the units here that's specified in these dense layers are telling us basically within each of those layers how many nodes are we going to have. So we have 128 nodes, and the activation function is ReLU, which is a common activation function for these types of classification, nonlinear classification type of problems, right? It's not like we're not predicting a continuous variable, like, for example, predicting somebody's height based on their body weight, mass, or something like that. Mm-hmm. So we have these 2 layers with 128 nodes each, and then we have an output layer. So the output layer is basically, hey, we've done all the work, we've optimized the weights for each of the variables coming into the model, we're ready to make a prediction, and we're going to put in this last output layer, layer dense. Its units are 9, and that has to be the exact number of outcome variables that we have. So in this case, we have 9 classes of pitches that we're trying to project or forecast a probability on based on our input variables. So we have 9 output layers, which will each receive a probability, and the activation function here is going to be softmax, which again is a common activation function that one might use for these types of classification problems. You can get pretty crazy reading about like activation functions and things like that. These are the most common. Feel free to play around and use or try different ones. Once we've specified that model, we need to define some of the learning information. So a neural network is also going to need some sort of optimization algorithm so that it knows, or so that as it's learning, it's trying to basically have some sort of measuring stick or benchmark to compare itself to and say, okay, am I doing better? What else can I learn? Am I doing better? What else can I learn? And it does that as each step goes by, which we're about to see in a second. So we chose an atom optimizer here. Again, this is a pretty common one. There's a number of different ones that you can use. And our loss metric or our metrics that we're using as our sort of benchmark here are going to be accuracy and then cross entropy. So basically like a sort of log loss type of metric, and we'll talk about that in a second. So we'll go ahead and run this. So now the model's all initialized and ready to go. All we need to do is get the data into the proper format. The data is going to need to be in a tensor format, which is sort of like matrices stacked on top of each other, and you can have different amounts of data and different depths of the tensor and things like that, right?
It's crazy how complicated it can get. Yeah, tensor is like a generic term for like an array where you can have a dimension of 0, which is like a scalar, a dimension of 1, which is like a vector, dimension of 2, which is like a matrix that we're used to seeing, dimension of 3, which is layers of data frames. You can have 4. Like, it's crazy. Like, I think the way that I like to think about it is like a layer of a 3-layer tensor, or a 3-dimension tensor is kind of like a movie. So you have the snapshots as you go. At least that's how I mentally visualize it. So we're going to set up our data to do this, and so it has to go through some specific transformations before we're able to feed it into the model, because that has a direct impact on the way that the model performs. And so we've done something similar to these two lines in the past, where we've converted our factor pitch type vector or column into a numeric. But this time we need to actually also convert it into a nice tensor so that our deep learning algorithm can use it. And we do this by wrapping it in a 2-categorical. So we first convert our factor into a numeric and subtract 1. That way it moves everything down 1, so now our numbers are from 0 to 8 as opposed to 1 to 9. This is important for the 2-categorical function, because what it does is it creates basically a dummy matrix for us, where each number that is in here is now a row, and the actual value it has represents which column it now has a 1 in. So let's take a quick peek. Let's run this and see what the head of train, cleaned, pitch, and type num, super descriptive name here. So we've got this data frame, or a matrix here, where the first row has a 1 in column 4. Now, I'm willing to bet that if we were to look at train, clean, pitch type,
the 4-seam fastball maybe,
and if we were to look at its first entry, it would be,
there it is.
It's the 4th entry in our levels here.
Yep.
There you go.
So now we basically, R makes it, or in this case, Keras makes it very simple to do your dummy coding. We didn't have to create each column ourselves and basically say, if it's a 4-seam fastball, put a 1 in column 4. If it's a changeup, put a 1 in column 1. It basically does this all for us.
So now we've got our output tensor, but we also need our input tensor. So what is the data that our model is going to be training on? And there's some very specific things you need to do to your data in order to actually do it as well. So there's a lot of setup for our models as well as training itself. So the first thing we did this in, I think, the 3rd or 2nd episode for
KNN.
For KNN.
No, UMAP, I think.
Or UMAP and KNN, where we actually need to scale our data, because the way that the algorithm works is if there is a large value and a very small value, that large value is basically, like, all you're doing is multiplying it by a weight. And so that large object is almost always going to drown out that small number, even if that small number is actually more predictive and more impactful. on the actual prediction.
And the key is that we want to scale our data, though, to the population that the model was built on, not just scaling it to, let's say we had a new data set tomorrow. We don't want to scale that data within that data set. We want to scale it to the mean and standard deviation of the population that we built the model on, because that's what we believe the population to be. This is probably also a reason why you want to continually check your models and update them for potential concept drift. Because if the population begins to change, then you need to potentially update the the mean and standard deviation, the descriptive values of that population.
All right, so let's step through all this stuff that we just talked about here. So we're going to create a function to assist us with scaling. So we're not going to use the basic scale function that comes in base R, because we want to do something slightly different from that. We want to be able to give the population mean and standard deviation and then have it be scaled. So basically what we're going to be doing is calculating a z-score from this. So we have the scale function here. X is the vector we're going to be scaling. A represents the mean of the population. S represents the standard deviation. And so we're going to be normalizing by subtracting the mean and then dividing by standard deviation to get our z-scores. So that's our function. We're now going to get those actual values that we're going to need to be using. So we're going to use our train data set here. We're going to remove pitch type, and then across each of the columns, so all the measurement values that we care about. So we're going to go across all those columns. We're going to get the average and the standard deviation. So we're going to pass a list. The function is going to apply as mean and SD, and it's going to create two columns, call and going to name the columns based off
name
of
them, yeah.
the function, the column name, and the function that is being applied to it.
Correct.
So
take a look at that.
Here we
there
go.
You go.
So like start speed, average, start speed, standard deviation, end speed, average, end speed, standard deviation. There we go.
Perfect.
All right. So now we're actually going to do the scaling and conversion into our nice little tensor for us to be using. Patrick, you want to take us through this one?
Yep. So we're going to do this on the clean data, and then we're going to do the same thing on we're going to do this on trained data, and then we're going to do the same thing on the test data. So the trained data, we're going to take our training data set that we created in the first step of this video. We're going to pipe in that we want to remove the pitch type column, because that really doesn't matter here. And we've already created our tensor of pitch type outcomes. So all we need for this is basically, that's why we called it trained cleaned X. We just need a data frame of all of our input variables. So we're going to get rid of pitch type, and now we're ready to do the normalization, the standardizing of the columns. So for each column, we're going to take the column name. We're going to keep the column names the same. We're going to use that scale function that we built just up above. And we're going to say, take that column, that's the X vector, and feed it the average of that column's average from the train set, from that train norms data frame up above, and then feed it the S variable, which is going to be the standard deviation. So we remember that the scale function takes an X, an A, and an S variable. It takes a vector, it takes an average, population average, and it takes a population standard deviation. We're literally going to do this for every single variable within our data set. So start speed, end speed, PFX, PFXZ, PXZ, XO, ZO, all of the variables.
XYZ.
The whole thing, exactly. So we're going to do that for all these variables, and then when we get done, we're going to turn it into this array and then into a matrix, because remember, we need to have this in a specific format for keras to run it, for TensorFlow to run it properly. So we're going to do that on the exact same steps on the test clean data set. Just notice that we're again using train norms average and train norms standard deviation. So again, we are using the population average and standard deviation of the data set that the model is going to be built on. So this test clean data set is a pretend data set that the model has never seen, and we want to be able to scale each variable to the population norms that were established on the data that the model was built on.
Perfect. Cool. All right. So now we get to the exciting piece, fitting the actual model. And so this is also very much unlike the normal training that you would do for a model, because the way that the models work is it actually gets trained on epochs. So each epoch represents one time that the model has seen your data. And when it's actually being trained, it doesn't look at the whole data set that you pass it. It actually batches them and does smaller iterations until it's seen the entire data set once, and then that's one epoch. So we're going to take our model object. We're now going to fit it using the fit function. The x argument that we're going to pass is the x tensor that we want to be passing to it. Y is the y tensor. So the two types of objects we just generated here. Now we're going to do actually something a little bit different. We're going to do a validation split. And so what that means is we're telling keras, hey, when we want you to actually do a split on the train data itself too, and separate it into a validation and an actual training within this as well too, so that we can actually view the progress as you go. So this is the validation split of 2. So this is going to take 20% to use as a validation data set. So
you can think of that as like a mini test set, and at the end of each epoch, or at the end of each batch, the model wants to see how well it did on the training set, and then see how well it did on this validation set, the mini test set, and then it gets smarter. So it says like, ooh, did we learn something, and can we update the weights of the data going into the model, into those hidden layers, and see if we can improve. And so that's what's going to happen.
Yep. Yeah, so now we're going to epochs. We set it to be 50. This is actually a tunable parameter. And so if you're doing a lot of, if you have more time to do this, this is something that you can actually mess with to figure out how many epochs you want to be using to train your model. Here we just threw in 50 because it seemed like a good number, and it was a good length for us to talk with you while it was being trained. And verbose equals 2. So this is actually the amount of information as it goes through each epoch that it gives me. So, because we want to monitor its progress as well. So let's run this and we'll get going. All right, so it's setting up a bunch of back-end stuff, and now it's going through, and it actually comes out with this handy dandy little plot over here on the right, so we don't have to worry about looking at the numbers over here on the left.
Yeah.
And so the blue line is the actual training data that's being fed, the 80% that's being fed, and the green line here is that validation set that we told it to hold out. And so
you could see the model is doing better on the data that it's built on, obviously the non-validation data in this case. So the accuracy is going up and the log loss is going down. So log loss is basically like, accuracy is sort of like this binary outcome, right? Where it's like you either predicted it right, yes or no. Log loss is a way to take into account the probabilities that you're actually predicting. So for example, if let's say we have a binary outcome and it's yes, you're sick, or no, you're not sick. If the model predicts that there's an 80% chance you're sick, it's credited as being a better model than if it predicted yes, you're being sick, but yes, you're sick, but there's a 55% chance that you're sick, right? So the closer it is to the actual outcome, the better log loss. And we'll go over this more when we talk about model checking. There's some math that you do to kind of arrive at the log loss, but it's a way to take into account the probabilities. Whereas if, for example, you had a binary outcome like accuracy that you were evaluating your model on, and that model basically says if it predicted 55% chance that you're sick and 95% chance that you're sick, both of those are considered a hit, even though the 55% is so substantially farther away from the actual outcome.
Yeah, so as you can see here, it was training. So at the very end of all these epochs, our accuracy on the trained data set, which is the actual data set that it was seeing, was at 82%, or 83%. So it was accurately predicting 83% of the pitches. But on the 20% held out that it wasn't trained on, it only got up to 69% accurate.
Yeah. it doesn't really improve across all of the epochs. If you look at our accuracy,
yeah, it actually like the log loss just gets worse and worse and worse.
Yeah, yeah.
And remember, this is data that it was very similarly trained on. So
yeah, and so and the reason why you have the validation set is to try and prevent overfitting. You want to ensure that, you know, if the validation and the accuracy, or sorry, if the validation and the training data set are moving in the same direction, they're both going down, that's, you know, that's potentially a good sign. If they start to diverge, or if they do different things, you might be nervous that, hey, they're in some way we're overfitting this.
Yeah. And so this is clearly overfitting.
Mm-hmm. Yeah, because it's going up while one is going down.
All right, so there would be a couple different ways you could approach this, but let's actually just look at the results itself. So we've trained now this model on 50 epochs. It actually did, I mean, if you just looked at the accuracy, hey, we're hitting 83% accurate. That's not too bad. But let's see how it does. So now we're going to actually train, or get the predictions of the output here. And so this was based off of Mike Parrott's suggestions in the YouTube comments from the last video. So thank you, Mike, for putting that in here. We took a little bit of editorial, made a couple editorial changes to make it work for us, but it was very much inspired by it. But thank you so much. So we take the model, we throw it into our predict, we put in the new test X data set, and we want type raw, so this will give us our raw predictions, and we're going to convert it into a data frame. So we can take a quick peek at that. So there you can go. So we have 9 columns. Each row represents a different pitch, and each one of these represents the I mean, I guess not direct probability, but how much it thinks this is the pitch. And so you can see here this pitch type for it thinks is 50.5.
0.5, right. For
so
seam
that is the highest class prediction that it has for it.
Right. So we want to be able to identify that.
So we're going to go through, we're going to take this data frame, we're going to set the names to be the actual pitch name itself so that it's a nice clean name that we can use. We're going to add in an IDX column, so this is the pitch index column, just so that we can keep that when we do this pivot longer. So now we're going to pivot longer and take all these predictions and kick it down long so that we can do a group by index. So now for each pitch, which value has the highest pitch prediction? And then we're going to mark that with the pred pitch column. We're going to now pivot back wider. So we pivoted longer to get, okay, now which row has the highest pitch, or which pitch type has the highest probability? Now we're going to go back to wide to keep it the way that it was before. We're going to ungroup because we had to group by index here. And then we're going to add in the original pitch type that came in test cleaned. So let's pop that. So there we go. So now we've got a data or a tibble here. So we've got pitch 1, predicted pitch was a 4-seam fastball, right? FF 4-seam fastball.
Yes.
Which
correct.
had the highest probability out of all of these, and the original pitch type was an FC.
Which is interesting because look how low the probability was for FC, right? 0.000.
It didn't think it was probable.
No. But interesting.
All right.
Yeah.
So now we've got this. So now we're going to throw it into our confusion matrix. So we're going to do a table between the predictions and the originals. Here we go. So this is like what we've been doing to, at a high level at least, evaluate all our pitches here. So the diagonal are the correct pitch predictions here. So we're doing pretty solid with the change up here, or no, change up CH. What's the CH
change up. And then the next one's cutter.
Cutter, yeah. Cutter actually did fairly well as well.
Mm-hmm.
FC, mediocre, got like 50% or so. Foreseen fastball, FF. That always seems to be the one where it does pretty well, but that is as you can see, the highest number of pitches. So it makes sense that it's like the models are always going to do well, just by the nature of if it basically defaults to foreseen fastball and then needs to have evidence to prove otherwise.
Yeah, class imbalance. When in doubt, guess foreseen fastball.
Yeah, exactly. FS didn't do super hot. FT did mediocre. So I don't know. It's interesting. So let's look at the overall accuracy and then the accuracy within pitch type. So we're going to sum the diagonal and against the total number of predictions here. So we actually hit an accuracy of 73.6%.
Pretty competitive with the other models that we had. We're around the same, 74 to 75%. So it's not too far off of what we had.
Yeah. I mean, we could look at the best we got was 76.
Yeah, so, with maybe the XG boost.
No, 76 was with the random forest.
The random forest. So, we'll have to look at them all.
Yeah, we will be looking at all of them together.
Yeah.
We don't have to just remember that. But yeah, so that's actually not too bad. But now let's look at the within pitch type. So we take our predictions, go, okay, what are the counts for your predicted and original pitch type? Now we group by the original pitch type to get, okay, what are the total number of pitches that exist for that original pitch type? And then what are the number that got guessed correctly? Is basically what's just going on here with all this code. We've used it multiple times in the past, explained it multiple times in the past.
Yeah.
So what we got here is with the change up, there are 1,678. We correctly guessed 1,368 with an accuracy of 0.815. Yay. Not bad. That's actually, I think that's one of the, that and with the curveball.
Yeah.
Or the cutter.
Cutter, yeah.
That actually, like, I think these did pretty well here, identifying those.
One thing we should have probably set the seed above our model, shouldn't we have?
Yeah, it's possible.
Does it matter for the? I can't remember if it matters.
It does because I think it initializes at a random number.
Yeah, it's a random starting point, isn't it? Anyway, you might. The point is you might get slightly the outcome shouldn't be so like egregiously different than what we got, but it might be slightly different. Yeah.
But yeah, just looking at this, like we're doing pretty solid here. It definitely lost a little bit on the foreseen fastball. We're only at 86.5% accurate. I think we're hovering closer to the 90s.
90s, yeah.
On that one. So that's interesting. And then the slider here is at 0.83 and the sinker is at 0.4. So those are doing better. Some of these like smaller classes, it's picking up on the nuance a little bit better.
Yeah.
On those.
And that's only with 2 layers. We might
2 layers, 50 epochs or epochs. I'm never quite sure which one is the correct one. If you can tell, I've been switching throughout the entire video.
Yeah, we might be able to do better if we add a layer, if we change the learning rate, if we change the optimizer. Right? We used Atom. We could use we could use like an adaptive optimizer that can optimize weights on individual inputs, lots of options. I guess the question with this is, did we do so much better with this more black box-ish model?
Did we solve all the problems of humanity?
Yeah, did we do so much better that it's better than, say, the random forest, where something that is maybe easier to less computing power, less time spent fitting the model, easier to explain, easier to extract information from. These are the types of questions you always have to kind of ask yourself when you do things like this. Is the steak worth the sizzle? Did doing all the extra work actually improve us by
a substantial amount.
A substantial amount, exactly.
Like if this model had hit like 90% accuracy,
yeah, that'd be different.
I would say that's pretty worth it. Like, yeah, we can't explain exactly what's going on under the hood to like if a pitching coach wanted to know, like, how do I get it to look more like this one? We couldn't tell you.
Right.
The model wouldn't be able to tell you. We'd have to do different interrogations on it.
Yes.
But here it's not doing better.
We're simply predicting a probability of an outcome. It's hard to know what's going on inside. It's hard to make any sort of like causal statement to a pitching coach. Like if you help this guy improve his Z movement, it will change his changeup or something like that. Like, it's hard to make those kinds of statements with a model like this. It's simply good for classifying the outcome. If, for example, the example that Ellis gave at the start, you didn't want to have the human sit back there and manually tag everything, this would be an option.
Which is why we did it.
Fair.
There we go. All right.
Perfect.
But I think that's it. That's deep learning at a high level. Definitely, if you're interested in this, do more research on this. There's a lot of publication, a lot of work going on in this field of just deep learning. I think it's very interesting, even though I'll probably never use it in my real world applications. But it's fun here.
Yeah, for sure.
To learn it. All right. With that, let's call it. As always, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name's Patrick Ward. You can find me on Twitter at OSPPatrick. And you can hit us both up on Twitter and retweet us at tidy_explained, or fire us an email at tidy.explained@gmail.com. Subscribe and comment on the YouTube channel if you have other questions, or open an issue in the GitHub repo if there's something that you might like to see in the future.
All right. With that, keep on exploring your world.